Fragmented, a podcast where we capture what's top of mind for Android developers. I'm your host, Kaushik. Today, I've got something really special in store. What if I told you every time you use a list in your Kotlin app, you could potentially see a 2 to 8x speed boost and a substantial reduction in memory usage? I'm talking of the order of 5x. This sounds almost too good to be true, right? Well, that's exactly what a new library called Immutable Arrays claims. Naturally, I was mildly skeptical too, but really curious. How are these benchmarks measured? What contributes to this performance boost? Is there some undiscovered magic that we have in Kotlin now? Are there any gotchas or caveats to when this is actually applicable versus not? To find out, I managed to track down the author of this library, Dan Rusu, and we had a fascinating conversation. I hadn't encountered Dan's work before, at least not in the Android circles that you and I probably frequent. So I was eager to pick his brain about both the library and what led him to create it. This is going to be an exciting episode. But before we dive into the interview, I wanted to revisit a few important key concepts that'll help you get the most out of this discussion that I'm about to have with Dan. The first is autoboxing and unboxing. The second is immutability. If you have already covered these concepts in the past or feel very comfortable with it, feel free to just jump ahead to the interview segment. I always label the chapters in the show notes for easy navigation. So, no offense taken. Feel free to jump to the interview piece directly. But if you need a refresher, let's break it down now. Autoboxing and unboxing. So when working with languages like Java or Kotlin on the JVM, we generally deal with two categories of types: primitive types and reference or object types. Now, with primitive types, these are your basic building blocks: int, char, for character, short, float, long, double, boolean. These are stored as simple values in memory and often kept directly on the stack. If you think about memory, there's the stack and the heap. These are kept directly on the stack, or, conceptually, you can think about these as being stored in the registers directly. They have fixed sizes and tend to be very memory and performance friendly. Reference or object types are slightly more complex, but thing that you're used to. They can hold additional metadata in addition to the primitive data values. There's more metadata that they can hold. What kinds of metadata? Functions or methods, and other probably nested structures. If you want to create a whole object-oriented programming world, well, this is where those objects come into play. They, on the other hand, are typically allocated on the heap, and you access them via references, so you don't directly access them like primitive types. A good example is integer in Java, and integer with a capital I, not int with the lowercase I, which represents the primitive. The capital I integer is an object version of that int. And effectively what it is it's an object that wraps the primitive int. By the way, Kotlin is a little interesting in this department. The language design tries to make all of this whole primitive/reference type appear seamless. So if you've noticed and you've written a lot of Kotlin code, there isn't a different version like in Java for a primitive int or an object or reference based int. They're all the same thing. It's just capital INT, and you go ahead, write INT, and the compiler, on the other hand, figures out when to use a primitive or a reference type underneath the hood. Okay, so why does all of this matter? Many collections, like one of the most important ones we typically work with, the data structure list, in Java or the Kotlin standard library, are designed to just store objects. They're not designed to store primitive values. If you want, say, a list of integers, a list of floats, you can't store raw int primitives directly into a list. You need to store them as integer objects in your list. In Kotlin too, by the way, when you put an int into, say a generic list of type T, it will be converted into this object version underneath the hood, or what we call autoboxed. This is convenient again. So you don't need to deal with, the differences of knowing when to use a primitive or when to use the object version. You almost typically never have to actually worry about this in the code that you write. But you totally can do this manual wrapping and unwrapping. But you probably have noticed in most of the code that you write that you don't need to. And this is because of this process called autoboxing. The compiler just knows what you're trying to do, and it adds the boilerplate to manually wrap and then unwrap your objects or primitives accordingly. But that process can introduce some overhead. And there's typically two kinds of overhead. One is the CPU work, and this is for the actual autoboxing and unboxing that you're doing. And the second is memory usage, because again, when you're storing a primitive versus storing an object, the memory implications are very different. Obviously storing a primitive is cheaper, so to speak, than storing the equivalent version of the object. Autoboxing is the part, by the way, where you wrap a primitive into an object, and unboxing is the part where you do the exact reverse. So if you just want to work with primitives. So hopefully this sets the stage a little for why, a specialized library that avoids these overheads can be so valuable. I'll also leave you with another tidbit that should spark your imagination when we discuss the library in detail. Arrays in Java and Kotlin are similar to lists in that, they are also like a collection data structure. You can store a bunch of things in them, but with one very big difference. Arrays can natively store primitive types, while lists typically cannot. Keep that in mind. There's obviously a lot of nuance to that, but just keep that in mind. Let's move on to the next topic, immutability. Immutability means once an object is created, it cannot change its internal state. To change it, you'd create a new instance with the updated values. Now, while this might sound not so efficient, when you look at it, immutability can dramatically simplify reasoning about state, especially in concurrent or multi-threaded environments like, hint, your Android app or any mobile app for that matter, where you do have to contend with a lot of these concurrent paradigms. If data never changed, though, after creation, say you created an object and could give a guarantee that it would never change, you eliminate a whole class of synchronization and concurrency related problems. This principle is at the core and embraced by many modern programming languages today. Modern architectures and frameworks, they like this idea of immutability because it just provides that guarantee and makes a whole bunch of reasoning simple. It also helps to know that you can pass data around without having to worry that, some other thread might swoop in and alter that object that you have or, mutate it, as they say, just before you even realize it. We actually did a really good episode on this in the past with Ryan Harter. This is episode 66, and he talked about immutability in some level of detail. This was, of course, back in the day with auto values, which is a thing that we no longer use. But I'll link to that episode in the show notes. If you listen to the first half, it does a very good job of explaining this whole concept of immutability and why it's important. All right, with these concepts fresh in our mind, let's turn our attention to our guest, Dan Rusu. He's here to talk to us about the library Immutable Arrays and how they might give your Kotlin code a very serious performance and memory edge over others. Without further ado, let's welcome Dan to the show.
Thank you. Thanks for having me on.
For those who haven't come across your work, especially because I don't know if you spend too much time in the Android development world, can you give us a quick introduction?
Yeah, so all of my time is spent on the back end, but I started looking into Kotlin in 2017 when Google announced support. So even though it was presented as an Android language, I'm like, hey, this compiles to JVM bytecode. This might be really cool for backend. So I started digging in and researching that and found that everywhere I looked, it was so well designed and architected. And many of the defects that I was seeing in backend, doing a lot of code reviews, I'm like, man, this just won't even compile with this type of defect. So I started compiling a list of defect categories that we come across in Java, but it just wouldn't exist in Kotlin. And I came up with a list of about 50 classes of defects. Oh, wow. For example, like null pointer exception is just one class of defect. And then I was like, 50 entire categories of defects. This is going to make a huge impact. So that's when we founded the Kotlin committee at Oracle. That's where I was at the time. And this was a huge 9-month effort to get Kotlin adopted at Oracle. And as you can imagine, Oracle, the creator of Java, probably wouldn't be too happy with us wanting to use Kotlin. But it was a huge success, and we got that adopted. The kind of bittersweet part about it is that 3 months after it was adopted, then I saw an awesome opportunity at Fair. And so I couldn't turn that down. And Fair was in the very early stages at the time. I was the second backend engineer. So we had an opportunity to really push in the Kotlin direction. They had started that before I got there, but it wasn't making momentum. And I had a lot of fun pushing Kotlin at both workplaces. So basically I'm hoping to use my passion for programming to make some sort of small impact in the world.
That sounds fantastic. Well, you seem to have already made huge impact with this library you're calling Immutable Arrays. I want to jump in and ask some questions directly because I feel this is so interesting and we're going to have quite some ground to cover here. What's the 5-minute pitch for this library? We already have arrays in Kotlin. What do I need this library for? And you alluded to this with those defect categories. Can you bridge that and tell us what's the pitch here?
Yeah, so arrays are generally not recommended in most Kotlin code bases. They're mutable. The APIs are very clunky. The code base is not clean and pleasant to work with. They also don't have proper working toString equals or hash code methods. And you think, someone's choosing arrays because they want the low-level hardcore performance. But most operations on arrays produce lists. So you lose all of that performance benefit that you're hoping to get. And then lists aren't a great option because they're very inefficient, especially when working with primitives, but also surprisingly, and most people aren't aware, but even working with reference types like strings or objects of any sort, lists are actually not that efficient with the way they work with memory. The main other thing is that in Kotlin, lists aren't actually immutable. They're just read-only.
Okay. I mean, already I have a bunch of questions there. What exactly does it mean for lists to be read-only and not immutable?
Yeah, so lists in Kotlin are actually backed by array lists and presented through the Kotlin list interface, which only exposes read-only operations. But if you cast it as an array list, then you have access to the underlying data type and you can just mutate it. So it's this kind of pretend to be immutable, but not really. And of course, lists aren't immutable at all. You can just swap the elements. So immutable arrays are kind of this impossible unicorn, where it's the best of both worlds. They're surprisingly much faster than arrays and safer than lists.
And in the project itself, you talk about true immutability, right? Is this how it bridges where with lists, you have this read-only mode? It's also kind of peculiar that lists have this read-only mode, right? Do you know the background behind it? Is this just because it was the quickest way to get some form of safe access to lists, but also allow mutations, which is the most common operations that we find with lists? Why this read-only mechanism?
So based on my understanding, I think that Kotlin's main concern at the beginning was just getting adoption. And there's been lots of languages that were attempted, and switching to a new language and throwing away existing ecosystems, that's too much of a hard sell. So by having something that works natively in the JVM world, where you can just make use of the Java standard library and the millions of existing libraries for Java, without having to have some sort of bridge layer where you convert from one collection type to another, that would just introduce too many memory and performance overheads. So I think this was the cleanest way of Kotlin coming into the JVM world and presenting something that's cleaner and usually safer.
I've covered some general ground on immutability, just before I had you on the show. You alluded to this. You said lists are not exactly very efficient with memory. Can you expand a little more on that? So why would arrays be more efficient with memory?
Yeah, so for one, lists operate on generic types. And generics are compiled to basically object in the Java world. So anything you store in there, whether it's the 8 types of primitives like int or boolean or floats, they have to be autoboxed in the wrapper types. And a reference to these wrapper objects is stored in the list. And that adds a lot of memory overhead. It might not seem like much. It's like, hey, I'll have a tiny little wrapper, but objects in the JVM world, you have the object header, which is like 12 or 16 bytes, depending on the JVM configuration. Then you have the actual data itself that you're trying to store. And then there's also padding to make it a multiple of 8 bytes. So all of this taken together for something like an integer or a float, the difference in memory impact versus an array that stores these floats in a contiguous section of memory versus a list of these floats, that's a 5x memory impact, even when you use pointer compression on the JVM. And without that, it's an 8x memory impact. So it's just, most people don't realize it's such a huge difference. And for something like Booleans, depending on how the Boolean wrappers are created, for example, in Java, if you call the constructor and pass the Boolean value, then you're looking at a 32x memory impact. Now, the JVM does try to cache small values, so like the Booleans and a tiny range of integers between negative 128 and 127. But even with these, it still ends up taking a lot more memory.
A large part of this is because of those objects. And because, if you step back and think about the concept of autoboxing and why you even have it, right? It is for these object wrappers, like lists, for example, natively work, a list of primitives don't make sense, right? You have a list of objects. And so that's how some of these boxing and unboxing mechanisms work. So with arrays, and feel free to correct me if I'm making any statement that isn't entirely accurate, but with arrays, you are able to store primitives, and therein comes some of those benefits, right? Am I understanding that correctly? Or do you have to do something with arrays itself to make them work with primitives?
That's exactly right. So with arrays, there are specialized versions of arrays for each type of primitive. Like you'd have a int array or a float array. And then there's also the generic version of arrays that stores any types of objects. So it's basically you have the 8 base types plus the generic type of arrays, whereas a list, you just have the generic version.
Ah, I see. And is this specific to Kotlin, or is this in general also the case with Java, where they internally have these representations differently?
Yeah, this is the same with Java as well. And I think Kotlin was trying to move away from thinking about primitives. So if you look at the Kotlin type system, you just have int. You don't have a primitive int type. And the Kotlin compiler, whenever it sees that, hey, this is an int and it's never nullable, let's use a primitive instead. So it makes use of a lot of these optimizations behind the scenes. But the memory overheads go even further than autoboxing because, for example, when you're copying values, you perform an operation take while you meet some condition. So, for example, take all the first elements of people that are adults, let's say. Well, to accumulate these values, you're appending them to an array list, one element at a time. The array list is backed by its own backing array, which auto-grows as you add elements.
Oh, that's true.
So this actually adds a lot of overhead because you also have all of the extra checks, am I at capacity? Do I need to grow the array? And then you add the elements to the array, which again does the balance checks on the JVM. Whereas with immutable arrays, you can take a lot of seemingly magical approaches that bypass a lot of this. So for example, with take while, you could find the cutoff point, and then you know exactly the size of the result, and then do a direct copy into a resulting array. So there's no auto-growing and creating garbage along the way.
So this is one of the follow-ups I have. In the past, I've spent a lot of time doing some levels of functional programming, like, with RxJava. And these days, of course, you have, flows, and, coroutines provides flows. And that API or that paradigm of using functional type operators makes a lot of sense. But I always thought like that was also one of the reasons that arrays didn't get popular, because the minute you move into that world where you have maps and filters and scans and transforms and all of these things, you kind of almost nudge yourself to using lists, because to your point, you can never predict the size based, like, the operation, only after the operation and the number of results, it makes sense. And the default go-to data structure for those purposes is an array list, right? Which is like expandable. And am I thinking about this correctly? So
yeah,
with immutable arrays, so to speak, even those operations can get easier because the predictability of those size is now more implicit.
Exactly. And even in the very best case scenario for array lists, where let's say you're performing a map operation, you know exactly the size of the resulting list. But so even though you set the initial capacity, so you don't have to auto grow the backing array, it's still checking are you at capacity every time you add an element? So as you're mapping each element, it keeps checking the capacity. And it's like, oh yeah, sure. No, it's fine. But you're doing extra work. Whereas immutable arrays skips all of that altogether. And it just transforms each element and doesn't perform that additional set of capacity checks for each element.
Oh, that's smart. I didn't even realize that when thinking about it from a face value, but that makes sense now. Okay. I have a really basic question, right? So, okay, you have arrays, you're saying immutable arrays. Okay, try to figure out a mechanism of just constructing immutable arrays, make sure that they are backed by, immutable objects. It doesn't feel that crazy a leap, but I look at some of those performance numbers and it's almost mind-blowing, right? Is there any other sort of magic sauce that you're doing besides just figuring out how to make these work or play together? Because that can't be it, right? Like there's clearly something else that's happening to get those performance numbers. My first, if I'm being honest, view of those performance numbers, and I'm like, this must be like some really hand-picked, cherry-picked case where it's working. It can't be that way. So can you talk more about that?
Yeah, so that's one of the things I struggled with at first, because some of my initial benchmarks had the results even faster. And then it raised too many red flags. People are like, there's something fishy here. So I had to actually look for operations that were a little bit more average. And those ones I'm seeing performance between 2 to 8 times faster. One of the techniques I'm using to get that is, just doing the bulk array copy operations instead of copying one element at a time. That by itself at least doubles performance in most cases, even when operating on reference types like strings or any objects.
Oh, wow. Interesting. Okay.
Yeah. So that's like an easy freebie. And I also use advanced Kotlin techniques. Like there's an experimental feature, override resolution by lambda return type, where something like if you do, let's say you have an immutable array of people where each person can have like their name and let's say their weight in kilograms and so on. So when you're operating on these types of objects, you're typically performing operations on their constituent primitive properties. For example, you might map the weight of all the people to get a immutable array of weights, and then you might want to analyze this to see what's the distribution and so on. In this case, I use the override resolution by lambda return type so that depending on the property that is being mapped, it automatically binds to the appropriate specialization, so that instead of creating a generic immutable array of float wrappers, I'm instead creating a primitive immutable float array. And that way it avoids the autoboxing there as well.
That's interesting. Let me just try to play that back to you and you tell me if I've understood it correctly, because that sounds really cool. I've never heard of this property, by the way, in Kotlin, the overload resolution by lambda return type. So you're saying typically, and this goes back to our initial reasons for needing autoboxing and unboxing at all, right?
Mm-hmm.
So if I have, say, a people array as your, a people list, which is typical, like, you do a database query, you get a list object with people. Now, people in itself is an object which probably has like some constituent primitive types, like, weight. You mentioned weight. Say weight is an integer for all practical purposes. That might be a float, whatever. But like, say weight is an integer.
Sure.
And now I do one of these operations that we talked about, like these functional operations, right? Where I have people and I map that. Typically, what would happen is, because the map operation results in a list in itself, that forces some kind of autoboxing where the int is autoboxed into an integer list, and then you run your operations. But what this overload resolution by lambda return type does, as you're suggesting, is it uses a more efficient data structure, like an array of say, or is that something that you did? Like, am I understanding that piece correctly?
Yeah, so basically, for the map operation, I have a version for each type of primitive that you work with. So it's kind of like map integers, map floats, but instead of having to think about, what method should I use in this case, that's too clunky. That's going back to like, Java style thinking, and it's just not a clean API. So instead, you just think about what operation you want to do. So you would say like people.map. And then as you're mapping whatever value, if that value happens to be a float, then it's going to auto bind to the float version of that method.
In terms of like this secret sauce again, right? Like, are there any other things? Because I noticed there's, in the README, you mentioned concepts around like, inline class, like compilation, like, and how that leads to like regular. Is this the same sort of concept? Are there any other like interesting magic sauce recipes that you have inside going on?
Well, good thing you bring it up. So immutable arrays are essentially inline classes which wrap regular arrays. So wraps a generic array as well as wraps each one of the primitive variants of the arrays. And but instead of having to think about like which type you want, you can just work with the API the way you work with lists. You would say, like you say, a list of like, 1 to 3. In the same way, you would say immutable array of 1 to 3, and it would automatically, based on the type of parameters, it would automatically bind to the most efficient version. So you don't have to think about any of that. And because these are inline classes, then at compile time, Kotlin replaces the usages where you reference the inline class directly and compiles down to a regular array behind the scenes.
Oh, and so that has that performance gain, basically.
Yeah, so it completely eliminates the overhead of the wrapper. So whereas array lists have the wrapper that introduce indirection, so whenever you're trying to get at the elements, first you have to follow the pointer to get to the array object, and then follow the pointer to get to the backing array, and then jump to the element. Whereas here, you have direct access to the backing array. So you get that bare metal performance where you have native access, and it's always the most efficient variant automatically selected for you.
We've been talking about performance a lot, so I just want to make clear to folks what are the kind of performance gains we're getting. When you think about performance, right? I use the generic word there. There's a speed boost, and then there's a memory efficiency, right? Like the less memory you use, obviously that results in better performance. Immutable arrays currently boast, just to be clear, 2 to 8 times faster. They're, in terms of speed, they're faster, 2 to 8 times faster than regular lists for most common operations. And you're saying based on, and these are the average benchmarks, so there are many cases where it could be even faster.
Yeah, sometimes it's like 40 times faster, but I didn't want to put that in the docs because that's going to sound too good to be true.
At that point, they're like, okay, I'm getting snake oil here. This can't be real. And the memory reduction you said is 5x, typical average time, right?
Yeah, so 5x when you're dealing with things like floats or integers. If you're dealing with smaller data types, it can be an even larger benefit. And the interesting thing there is that it's much more than just because we're avoiding the wrappers, then we're using less memory. But the very act that these are immutable data structures allows another like complete level of efficiency gains where, for example, let's say you're saying, okay, I have my list of people and filter to get only the adults or something like that. Well, if all of them are already adults, then these operations on immutable arrays, instead of giving you a copy of all of the same elements, it just returns the exact same immutable array because it's mutable, it's safe to be shared.
Makes sense.
Yeah, there's dozens of these. Actually, there's hundreds of scenarios where this types of optimizations take place, where if you get back the same elements or if you get back 0 elements, then it uses exactly 0 additional memory that is being held onto. Some of these might accumulate elements, and then it figures out, oh, actually it's the same. So then it discards those and it retains 0 extra memory.
Okay. I'm learning so much. This is great. Another question I had is, how do you go about measuring these performance gains, right? Like, just for someone who's curious, how would I go and do some of these equivalent measurements?
Yeah, this is a really tricky one. So getting into benchmarks, it was kind of like a huge rabbit hole. I ended up spending 2 months reading everything about JVM performance, pitfalls, and best practices. And I landed upon the Java micro benchmark hardness, which most people refer to as just JMH. And that's the de facto standard for doing proper benchmarks on the JVM. That accounts for things like JIT warm-up and various things that, depending on the order of operations, you would get different results. And this avoids those kind of misconceptions. So I'm using JMH. I also created a standalone repo where I import the library as a regular dependency. So that way I don't have any access to library internals. I'm using it the way anyone else would use the library. So I wanted to make sure it's as pure a comparison as possible. And there's also a lot of things where the initial approach would be like, oh, okay, let's create a collection of a bunch of data and let's perform some operation on it repeatedly to see how many times I can do it per second. And that sounds good, but that actually falls into a different category of misconceptions where that data, because of your operation, because it's memory bound, it's slow. But after the first time that you access the elements, everything is in tiny L1 CPU cache, and then everything is quick. So it makes it look like, oh, it's better than it is. So to get around these type of things, I ended up creating 1,000 different random collections. And each of these collections has a random size with a probability distribution that mimics what you would see in the real world. For example, you'd have something like 35% of collections might be just like less than 10 elements, and you have a tiny percent that are very large, and so on. So it tries to create random data sets that are very representative. And the randomness also avoids the CPU branch predictor from catching on to patterns and optimizing things away. So basically, I have tons of random collections created, and then I perform the operation on each collection. And that way, I'm always operating on a fresh collection. It's not cached in a tiny L1 cache, and it's representative of real-world benchmarks. So I swap between lists, regular arrays, and immutable arrays. And because immutable arrays naturally work with all primitive types without the developer having to think about it, then I also test every single type of data type, the 8 base types plus a generic string type. And I perform these operations on all of them. So it's like 27 combinations for each operation, and repeat that and make sure that I get low margins of error and so on. So it's really difficult. It was a 2-month process, but I was surprised with the results.
Yeah, no, and it sounds like a lot of thoughtful work done on the performance and adds a lot of credibility to some of these benchmarks that you've stated. So thank you for that work. And I'll try to link to a lot of the stuff that you said, the standalone repo. If those are publicly available, I'll make sure to link to all of those.
It is.
Fantastic.
Yeah.
So we talked about benchmarks. We talked about like what the purpose of the library itself is. One of the things I want to touch on, which also seemed like a very important aspect to using arrays, is API design. A quick background. The reason I even stumbled upon your library was this year's advent of code. I think it was day 2 or 3, had this concept of you needed to use like a matrix. You can go and look at the problem. And the only way to do it in Kotlin is using a 2D array, right? Like, so an array of array. The API itself is super clunky. I stuck with it because, I didn't want to like go down a rabbit hole. I just wanted to solve the issue for the day. But afterwards, I came back and I'm like, why is it so clunky to use arrays? And so actually that's how I went about looking and searching. And, down that rabbit hole of research is where I ran into immutable arrays. And I noticed that you've tried to make it as pleasant to use with lists. Now, lists, I actually think work great as an API, right? Like, I've not had too many complaints.
Yeah.
Arrays is terrible. If, I remember in the past, I've chosen to use a list knowing fully well that the performance gain is going to be lost just because the API was so horrible to work with, right? Mm-hmm. How did you think about that? Because it looks like immutable arrays almost is the same as the list API design. You've put a lot of thought into that. Can you talk more towards that?
Yeah, so that was one of my guiding principles for immutable arrays. I see most libraries, you get a clean library, it's really nice to use, but when you want more performance or efficiency, then you have to sacrifice readability and you have to call specialized methods and you have to, know and understand that. And that just adds a lot of mental overhead and complexity that you have to always think about. So I wanted something that felt exactly like lists. I don't want the user to have to think about like, oh, which specialization do I want to use, which optimization, which version of this method. So I've taken advantage of a lot of Kotlin features that wouldn't be possible in Java. For example, I have multiple functions that have the same signature. They just differ in the generic type parameter. And something like that wouldn't even compile in Java. But for immutable arrays, I'm using JVM name to specify unique names. And that way I can have the same function with the same clean name, which compiles to unique names in the bytecode. And so as developers, you just think about what do you want to do? Oh, I want to create an immutable array of people. And you just create it the way you would create a list of people. Except that you say immutable array of instead of list of. But aside from that, the rest of the API looks practically identical to using a list.
Yeah, and I specifically like this because one of the other problems, right, in Kotlin at least, you have array of int, that's possible. Mm-hmm. Then you have int array, right? And it goes back to some of those things where if I'm a developer, I don't really want to think whether I should be using array of int or int array or float array or like the different things. I just want it to do the right thing, and it goes towards like some of these things, which list kind of does, right? You can, it's like a grab bag of just throw whatever you want in there and then it'll do the right thing or as right as it can.
Yeah. And then the other thing I wanted to accomplish was I wanted to make sure that you can use immutable arrays in existing projects without having to do like a big bang, like replace all lists with immutable arrays. That's like too much of an ask. So immutable arrays have a couple of ways to make them easily interop with list APIs. So when you have an immutable array of people or whatever type of data type, you can call toList to create a copy into a standalone list, or you can call asList to create a wrapper that wraps the same immutable array backing array and just exposes it as a list without copying the backing array elements. So it's basically a constant time way of exposing immutable arrays without performance or memory overhead. And there's also as iterable, the same type of wrapper without copying the elements. So it's really easy to gradually introduce into existing code base you would work with immutable arrays in your class or your package or maybe your module. And then the boundary layers where you interact with other parts of the application, in those places, you expose it through these list-friendly functions.
Okay, I'm sold. I want these gains. I want the API, clean APIs. How do I go about migrating my project? And you already pointed to some very interesting things there on how I should be going about this. And the way I was thinking about it is there are always going to be those, and you mentioned API boundaries, like as an Android developer, sometimes maybe, my compose list only takes a list function. So at some point, I will need to transform these things to a list. But as you're suggesting, you can internally operate with immutable arrays, do all the do all the operations, reap the gains that you get from using immutable arrays from a performance perspective. And right before you're going to surface that result, you can transform it to a list. And then with those boundaries where you don't have an option, where those APIs don't take immutable arrays, you can just go back to using a list. And it's as simple as a to list or an as list.
Yeah, and with as list, it's like zero performance impact essentially, because it just creates a tiny wrapper without copying the elements. So that's a really nice and easy way to expose it.
Interesting. And maybe I missed this nuance. What is the difference between to list and as list?
So to list creates a standalone list with a copy of all the elements, whereas as list creates a wrapper that implements the list interface.
I see.
But doesn't copy the backing array. It just references the same backing array. So when you're using that list wrapper to get some element, you're actually jumping back to the same array without storing a separate copy.
Interesting. And because they're immutable, it gives you the advantage of playing with this more safely. You don't have to worry about potential other repercussions.
Exactly. Yeah, it's completely safe. And immutability adds a lot of these performance benefits.
You've given a lot of time. Thank you so much. Before we wind this down, I want to talk about the caveats. So what do I need to make sure when I start to use immutable arrays in my project? Is there anything that I should watch out for or be careful here?
Mm-hmm. Yeah. So immutable arrays are not fully immutable all the way down. So they're only shallow. They only provide shallow immutability. So let's say if you have an immutable array of people, yes, you can't replace the people elements in your immutable array, but maybe your person class has mutating methods to mutate properties of the person. So you can still mutate the underlying objects that you're storing. You just can't change the collection itself.
Right. And this is the level that you talk about. Immutable arrays, your library adds another level of immutability one layer down. But again, if you go to the nuts and bolts for the actual data objects, if those are at some point immutable.
Yeah. So if you can change the spouse of the people or whatnot, see, when you're sharing objects, it's safe to share these collections, but also keep in mind that the underlying objects themselves, if you don't want someone to mutate them, then you have to think about that separately. Yeah. And there's also two other things to keep in mind. One, this library makes use of two experimental Kotlin features. So the overload resolution by lambda return type, it's a really cool experimental feature. It's been around in Kotlin a long time, since Kotlin 1.4. So it's fairly stable. It's used extensively by the Kotlin standard library. A lot of their utilities make use of it, but it is an experimental feature. And the other experimental feature I make use of is the ability to override equals and hash code for inline value classes. And this was added to Kotlin 1.9. If you're not allowed to use any experimental features, then maybe you would limit usage to side projects. But this is just something to keep in mind.
Makes sense. Thank you for calling that out. And this made me think, why doesn't JetBrains just include this in Kotlin, right? It feels obvious enough where some of these gains, more often than not, I can barely see the downside. Why do you think they haven't just, graduated this kind of functionality into the native standard library?
Yeah, that's a good question. I think there's a lot more things that have a lot more weight On JetBrains, for example, their multi-platform effort is a huge one.
That's fair.
So in terms of where do we get the most value for Kotlin developers, I can see how JetBrains would see other places that would provide more value to the general public. And whereas this is one of those things that maybe would be several years down the line that they might want to look at.
Makes sense. And it's a good call out because I know a lot of people right now are constantly looking at, Kotlin multi-platform. Array lists right now don't support Kotlin multi-platform, right? Because you're playing very deeply with the Java JVM at this point.
Mm-hmm. Yeah, so multi-platform Kotlin needs to have their own separate collections.
Got it. Oh, so yeah, you could potentially build the equivalents in each multi-platform implementation, but that just, again, is more effort that will be needed.
Yeah, I'm hoping. So the ability to override equals in hash code for inline classes. Unfortunately, Kotlin only added this to the backend compiler, which handles both Android and standard backend JVM applications. If they also add this to multi-platform, then that would allow me to look at making this a multi-platform library, and then people could use it there. But that's the key limiting thing that's preventing immutable arrays from approaching multi-platform.
Got it. And that sounds like common enough where it feels like down the line you might need that, right? It's because it's so core a requirement where you're overriding things like equals and hash code.
Yeah, so I think they were intending to add it, and then the efforts with releasing K2 kind of delayed, or they dragged on a little longer. So my opinion is that JetBrains probably pulled teams in to focus on K2, which I think is the right decision, and get that out the door. And now that K2 has been out for a while, now I think they can start going back to tackling this.
Makes sense. K2 being the new compiler that they use, the Kotlin level. I'll make sure to link some notes to that as well. Dan, this was fantastic. You've got me excited. I'm like eyeing all my side projects now. I can start to swap, the library pretty easily. If I run into problems or I have questions, what's a good way people can reach out to you?
Maybe the easiest to remember is danrusu.com, DANRUSU.com. And that has a link to the repo that I'm calling Performance-Oriented Data Structures for Kotlin. And this repo contains immutable arrays. Or in GitHub, if you search Performance-Oriented Data Structures for Kotlin, or pods for K for short, then you should also be able to find it there. And you can create issues or feature requests. And I would love all feedback and suggestions and recommendations.
That makes perfect sense. So the GitHub repo, we can add issues and, spawn discussions there. That's a great place for contacting you. Mm-hmm. Dan, thank you so much. I appreciate you giving me this time, and I'm sure our listeners will as well.
Yeah, thank you for having me. It's been great.
All right. That was fascinating. I hope today's deep dive got you thinking about the underlying costs of autoboxing and the benefits of immutable data structures. Just understanding these fundamentals can really change how you think about, designing data-intensive applications and mobile apps. As we wrap up this episode, our last for the year 2024, I want to thank you all for listening, for supporting Fragmented, especially as we've gone through this reboot, and for sticking with me as I continue to explore new and exciting topics and where to take the show. Have a wonderful holiday season. Spend time with your loved ones, recharge, and I'll see you in 2025 with more episodes, more insights, and more Android goodness. Thank you all for listening, and I'll catch you in the next episode.